Hello, friends. We are going to talk about 4.9 in this video. And the learning goals for 4.9 are basically to know what we mean and how to find the most general antiderivative of basic functions. We're going to be able to check antiderivatives by taking the derivative or by differentiating. We're going to apply antiderivatives to solve what are called initial value problems. Okay, and so I want you to do this warm-up. If you can take a moment, maybe pause the video, do this warm-up. I think it will give you a good idea of what this whole section is about. And I'll go over it in just a moment. Okay. Maybe you paused the video and tried it. Good. Let's talk about it. Number one, think about a function whose derivative is equal to 2x. Do we know what it is? So if I have over here something like f prime of this thing is equal to 2x. Do we know what function has a derivative equal to 2x? Yes, we do. F of x would equal x squared. That's an example. If my function is equal to, if my function is such that when I take the derivative, I get this thing back, and we say this is n1 particular an antiderivative of derivative of 2x. So instead of going forward in this process, we're now going backward. We're starting from a derivative and finding the function. Okay. Now notice something else though, which is that had I added something to this, like say +7, wouldn't this also, if I take this derivative going forward, right, it would have been +0, and so it would have been the same. So there's a thing that happens when we take the derivative, and anything that's constant goes to 0. Therefore, when I take an antiderivative, there's sort of like a mysterious constant. So look, I know x squared works, but I can think of another x squared plus a constant works as a function who, if you take the derivative, you get 2x. So let's take the derivative. Let's do a number 3. Do number 3 and see what happens. See if we can see a pattern in f of x equals x cubed plus something. What is f prime? That constant goes to 0, and I get 3x squared. Right? And then, in fact, if you do all of these, you'll get 3x squared. All of these values. So this was 3, 1, 2, 3, 4. All of these different functions have the same derivative. And at this point, if you see a pattern, you can guess the most general antiderivative of some other basic function. So what is f of x if our big capital F prime of x is equal to just x squared? I know that if I take the derivative of x cubed, I get a 3 times x squared. So if I'm taking the antiderivative of x squared, let's just try it. Let's try it. Let's try capital F of x, and instead of multiplying by 3, let's divide by 3, aka plus any constant k. Let's see what happens. F prime of x is equal to, the 3 comes down, cancels that 1/3. Isn't this going to be 1/3 times 3x squared plus 0. And these things will cancel out. We get x squared plus, we just get x squared, okay? So this right here is what we call the general antiderivative of x squared, the function x squared. Not x cubed, x squared, there. Where k is some constant. And in fact, it's any real number constant. Okay, so any function that looks like this, their derivative will be x squared. And just like the power rule, when we take the derivatives, we take this thing down and multiply. The inverse power rule will mean that we increase the exponent and divide, okay? Now, this was all just supposed to be examples. Those examples were supposed to sort of help you get familiar with the patterns that we're going to be using when we look at antiderivative equations. And that's really the heart of it, is that you're looking for something that when you take the derivative, you get some goal, right? So you have a function and you want to know who is that the derivative of? I have the derivative, and I want to know where that derivative came from. Physically and in context, that's sort of like I know the velocity or the rate at which something is traveling, and I want to recover its position, its actual distance or location from the velocity. Suppose I want to measure, suppose I can know using a device the variable rate at which water is leaking from something. And we want to take that information and turn it into information about the total amount that has leaked out. A biologist knows how fast bacteria increase, and therefore from that would want to say how big is the population. So in this case, in antiderivatives, we're going from rates of change to sort of total values. And this, in fact, will be related to the fundamental theorem of calculus, right? This is an antiderivative idea. So technical definition, a function f is called an antiderivative of f on some interval, because we can think about this happening on just like a specific part of the domain, but we won't worry too much about that in this class. Technically, we need to say that, but really it's just the function. It's the function capital F. We call it an antiderivative if its derivative equals the little f. So it's so this capital F is called an antiderivative of the little f. Okay, so we explored this example, right? It wasn't hard to discover if I have a little f of x squared, what's that capital F? Well, we know that if I have an x cubed and I take the derivative of 3 comes down. So what I want to do is start off with a 1/3 in front. That'll cancel out. So when I take the derivative, it'll become just a 1x squared. And so the most general antiderivative of x squared is that, where c is any constant. Okay. When you see the words most general antiderivative, it means that you're going to have to add some constant, some unknown constant, that you don't know what that constant is for the antiderivative, because it could have been anything. Because as soon as you take the derivative, it goes away. So this is the plus c that you don't want to forget when you're just doing what we call a general antiderivative, or as we'll see later, an indefinite integral. Okay. Now, if we explored this somewhat with the curve sketching, but basically any function of this shape would have a slope story equal to x squared. So all of these functions, if you say they're slope stories, they'll have the same derivative, y equals x squared. So for any one of these colors. So you can shift a graph up and down and it doesn't change the slope story. So that's why we always want to be aware when we do an antiderivative, there's some constant, because it could be there. And we may need that constant, but only if we have some other information. It's just interesting to think about how many different curves could have the same function for its derivative. So let's think about general antiderivatives of these things, which means I want to find a function where if I took the derivative, it would end up as this function right here. So what function, if I take the derivative, gives me sine of x? Well, let's try f of x equals cosine of x. Does anybody remember what f prime is then? What would f prime be? Isn't it a negative sine of x? Therefore, what I'm thinking is I want this to end up being a plus, right? Because I want my little f of x to equal that. So if this ends up being a plus, I need to put a minus in the original antiderivative. Sorry, this is a capital F. This is supposed to be a capital F. And we're just using capital letters to denote antiderivatives, right? But if I put a minus sign and say that the antiderivative is minus cosine, when I take the derivative of that, then the minus signs will cancel out and I'll get a positive sine of x. So if f of x equals sine of x, then my capital F of x, the antiderivative, is going to be minus cosine x, and of course plus any constant. Now 1 over x, it's the result of using something and ending up with a -1. And now remember, this is not, we're not taking the derivative of this, we're taking the antiderivative of this. Do you remember some function whose derivative is equal to 1 over x? You may remember. You take the derivative of, and it equals 1 over x. Well, it turns out that that function is the natural log of x. And sometimes you can just remember it, okay? So I'm going to write down natural log of x plus c, but there's actually much more to it, which is that for any x value, you need to put absolute value signs around that. For any negative or positive, it's not defined at 0, but you can have negative x values and still get that antiderivative. This last one here is what we call the inverse power rule, and it looks like this. What we do is we increase the n by 1, and then we divide by that number, right? When we did this with, remember when this was a 2, we ended up with a cube, x to the cube divided by 3. So we increase that exponent by 1, not an n plus 2, no. And we divide by that same number. Then we add some constant. You can also write it like this, where, because this is a constant, n plus 1, times x to the n plus 1 plus c, okay? And this is called the inverse power rule, which is, it's because it's the inverse process of taking the derivative of a power function. Now we're finding the antiderivative of a power function. Okay. Here they explain about the same thing I did. They said, if you take the derivative of this, you get sine of x. Therefore, that's the most general antiderivative. Here we remember that the derivative of natural log of x is equal to 1 over x. And this is true only for, remember, the domain of the natural log function, which is x strictly greater than 0. But if we're going in the opposite direction, right, 1 over x is defined everywhere except at 0. So we actually can have negative x values as well. And you get that the most general antiderivative of 1 over x is this natural log of the absolute value of x. And this is going to work, it works for x less than 0, too. Here's actually the most general antiderivative. You can split this function into 2 parts. And there's an interesting video by Jim Fowler if you're interested in why that's true, but I'm not going to dwell on it too much. Here is the inverse power rule, very important. So we need to do some examples now. Oh, here's a table of functions and their antiderivatives, basic antiderivatives. To make them general, you just add a constant and then you get a very general, you get the most general one. But what this is saying is that if I have a constant times a function, the antiderivative is just going to be a constant times the antiderivative. If I have a sum of 2 functions, then the antiderivative is just the sum of the antiderivatives. If I have a power function, except when n is equal to -1, we just do this inverse power rule, and so on. The antiderivative of e to the x is e to the x. The antiderivative of some log base b, not equal, for any base of a, sorry, not log, the derivative of any exponential base, any exponential function, is you divide by the natural log of b. If I start with cosine x and I take the antiderivative, I get sine x, and so on. These, everyone's favorite, these trig derivatives. If I start with secant squared, the antiderivative is tangent. If I start with secant tangent, the antiderivative is secant. Because if I take these derivatives in this direction, right, derivative of secant is secant tangent, derivative of tangent is secant squared, and so on. Some to just recognize, I think we derived this one, but a lot of these are just formulas you just look up and remember. We didn't cover these, but these are the hyperbolic sine and cosine. This is in, and I never, I never ended up using these very much in my mathematical career, and when I did, I just looked them up. But you can see 3.11 if you are interested in those. Point is, though, is that here's a new table of things we want to refer to, and these will help us undo differentiation. They'll help us go in the opposite direction of finding the derivative. All right, came down here to some homework problems so we can practice what we just learned. We're looking for the most general antiderivative of the function. This is problem 5. What I'm going to do is I'm going to make this look like stuff we recognize. In fact, what I notice here is this is a sum of a bunch of power functions, right? So if I take the antiderivative of this, then I end up with I have to increase that exponent and divide by whatever that new exponent is, or multiply by 1 divided by it. So I'm going to rewrite this function here and say, what are these exponents? Here now, the inverse power rule, we're going to be adding 1 to those fractions. I'm going to use this capital F of x. And essentially what I'm going to do is write down the plan. And this thing, by the way, is going to have some big plus C on the end. So we know it's the most general. So I have to account for some constant. So what I'm going to do is I'm going to leave the constants here in front. And I'm going to say that this whole thing is going to be divided by 2/5 plus 1. And x is going to be raised to the 2/5 plus 1. And that's my 7 times x term, plus I'm going to have my 6x to the negative 4/5 divided by negative 4/5 plus 1. Now what you do is you simplify this. Oh, I have to add 1 in there too. And it turns out to be fraction math. But remember that if you're adding 1, it's really easy. Plus 5/5, meaning this thing becomes 7/5. The other thing to remember is that if I'm dividing by 7/5, you just flip the fraction over. And so this becomes 5/7. Okay, so you end up with a function where the exponent gets multiplied. So the exponent, if the exponent is 7/5, you're multiplying the outside by the reciprocal. And in this case here is negative 4/5. Plus 1 is the same thing as adding 5/5. And that just means this is positive 1/5, right? And therefore I'm going to multiply by the reciprocal of that, and it's going to become 5. So I'm going to show one more. I'll show a little more work over here for my friends who are still working on this algebra. Almost done. We're almost done. This becomes 7x to the 7/5 divided by, and I'm only going to do this once because in general I want us to get better at, well, I'll do it if you need it, but here is 6x to the 1/5. What are we dividing by? 1/5. Now we can take those reciprocals and multiply. These are now just going to be my original constant in front, 7 times the reciprocal 5/7, okay, plus this new power function, x to the 7/5. Ooh. That reciprocal is going to be 5/1, or 6 times 5, x to the 1/5 power. And there's a plus c all the way down. And so our final answer, we simplify these things. Notice, oh, the 7 cancels. This becomes a 30. We have our answer. F of x is equal to 5 times x to the 7/5 plus 30 x to the 1/5 plus our constant c. That is the most general antiderivative of our original function here, which was 7x to the 2/5 plus 6x to the negative 4/5. And if you take the derivative, you can confirm this, right? So the way that we check, right? The way that we check is to find f prime of x from our answer. And that'll be, and I'm just going to write this out one time. So I have 5 times, right, 7/5 comes down. And then we have x. Have x to the 7/5 minus 1 plus the negative 4/5 comes down. Hold on. Okay. So we're checking to see if this little f of x that we started with is the same as the derivative of our answer. And what we're going to do is we look at this function. Now it would be, sorry, a positive 1/5 would come down and multiply that times x raised to the 1/5, and we would subtract 1 from the 1/5 like that. Okay, and our constant c would be 0. So I'm going to put a plus 0 just to remind us. And also, I made a mistake because my answer here had a 30 here, not a 6. There. Okay. So I'm taking the derivative of this answer. It's kind of like Jeopardy, where the function they gave you was the derivative answer, and what you're trying to find is the question. What function's derivative is 7x to the 2/5 plus 6x to the negative 4/5? Well, we're just checking that it's 5x to the 7/5 plus 30x to the 1/5 plus a constant. And we end up with, yes, the same thing. 7/5 minus 5/5 is 2/5. 30 divided by 5 is 6. And 1/5 minus 5/5 is negative 4/5. Bada boom, bada bing, forget about it. Okay. So we checked our answer by taking the derivative. Okay. I want you all to try this one on your own. What we're going to do first is, and I'll just give you a hint. First, I want to write this function all in terms of a single exponent on each variable. So x is going to be what? 2/7. This is the first power. That's the 1/2 power. So I end up with a plus x to the 1 plus 1/2. And I want you to take a moment, pause this video, and do this problem on your own. Okay, I'll show you the solution now. What we do is we take that original function, we're going to add 1 to those exponents. We're going to divide by that to get our new antiderivative. And we have 3/2 plus 1. Now I just need to do those fractions. Okay, we're using this inverse power rule right here. I just need to remember what's 2/7 plus 1 is 2/7 plus 7/7 is going to equal 9/7. 3/2 plus 1, 2/2 again is going to be 5/2. Okay. So what I end up doing, and I'm going to do a shortcut now, is I end up with the reciprocal of these things in the front, because I'm dividing by 9/7. So that's the same thing as multiplying by 7/9. I'm dividing by 5/2, so that's the same thing as multiplying by 2/5. And I have still power functions. We're adding the two things, and we have in the numerator, sorry, in the exponent 9/7 and 5/2. Okay. So for the final answer, you would write, because they ask for the most general, you would write a plus c. So let's write the final answer. 7/9 x to the 9/7 plus 2/5 x to the 5/2 plus c. Okay. Now, again, you're going to want to do the same kind of algebra. So I'm going to just give you a hint. This becomes 7 times t to the negative 1/2. Then I have what? T to the 1 minus 1/2. Then I have t squared minus 1/2. That is what you're going to start with. And then you'll use the inverse power rule. Now, there is a process now, so like in number 15, where I have multiple derivatives. I'm given the triple derivative of something, and I want to find the actual function. What we're going to do is repeat that antiderivative process over and over and over again. Actually, you're going to repeat it 3 times to get to the original function f of t. Okay, so if I do my antiderivatives, then I can remove one of my primes. So one prime removal is going to be, I had t to the 1/2, and I had, look, notice it's minus cosine. So the antiderivative is just going to be sine. So this is going to be plus 6, and this one becomes sine t. And I have to add 1 to the exponent here, and then divide by 1/2 plus 1. So now I know what my f double prime is. It's 1/2 plus 1 is 3/2. So this one's going to be upside down, 2/3, t to the 3/2. Plus, oh, you know what? It's not plus. The antiderivative of cosine is just sine, so it's minus, like 6 sine t. So this is my second derivative. And if you need a reminder, you can go up to this table, or you can look it up. I'm going to go up to the table, say, what was that? What was that? What were those antiderivatives again? There it is. So the antiderivative of sine is minus cosine. I was taking the antiderivative of cosine, and that's why it just stayed sine. Because when I go back, when I take the derivative, it just has to be cosine. Okay. It can get confusing which way you're going. Just remember that in this section, you're always looking for antiderivatives, which means if you take the derivative, you should get what you started with. So if I take the derivative of this new function, f double prime of t, I should end up with what I started with over here. Now we do it one more time. In fact, we need to do it 2 more times. If I want to take off the prime, I'm going to apply the power rule again. So I'm going to write t to the 3/2. Right? I'm going to have a 2/3 in the front. This is all going to be divided by this thing plus 1, 3/2 plus 1. And then I have to remember, what's the antiderivative of sine? It's minus cosine. So let me write it. Let me write that for you like this. So this thing becomes minus cosine of t, and all I did was just look up that antiderivative formula. Now I'm dealing with the fractions, and I get 3/2 plus 1. It's going to be 3/2 plus 2/2 is 5/2. So I know that my I know that this simplifies to, this is going to equal, I have, this is going to be 2/3 t to the 5/2. And now in front, this reciprocal of that, that's 5/2. Now this is going to be 2/5. And then this is going to become plus, because there's a minus times a minus, 6 cosine t. Now, one last thing I forgot, when I took that first antiderivative, there's a plus c, right? So when I got my f double prime, that's a plus c. So if I remove 1 prime, I actually have, what's the antiderivative of a constant? Well, what has the derivative of a that equals a constant? A linear thing. So this becomes c times the variable t. And then I need to add one more constant again, and we're calling that d. So the answer for f prime, or which is now the second antiderivative, if I start this over again, trying to write a little more clearly, let me consolidate my work. Consolidating my work, this right here was plus ct plus some other constant d. Now I end up with f prime of t is going to equal, it's going to be 4/15 t to the 5 halves plus 6 cosine t plus c times t plus d. Wow, we went from the third derivative of a function, f triple prime, and we've applied the power rule twice to this first term here, the inverse power rule. We've been using the trig antiderivatives. We used that twice, and we also needed to add a constant for each time we took the antiderivative. And notice in the instructions it says use c for the constant of the first derivative. That's this one. Sorry, first antiderivative. And d for the constant of the second antiderivative, which we did here. And if I'm a little more consistent with my color coding, it would have become red there because I should add it at that line. Now we have to do one final antiderivative to this one. And what are we going to do? Well, first I'm going to copy down this power function to show how I'm going to use the inverse power rule. I'm going to say this is going to be 4/15 t to the 5 halves. I'm going to have plus 6 times whatever the antiderivative of cosine is, plus, now my constant c, remember this is now t to the first, c t to the first power. This is kind of like a t to the 0th power here. You remember our t to the 0th power is equal to 1. So it's kind of there. I'm going to write it here as our d times t to the 0th power. Now in red, I'm going to write in all my antiderivative process, which is I add 1 to the exponent, I divide the whole thing by that result. If I take the derivative of something, what is cosine? Well, I think I need another, no, the derivative of sine is cosine, so the antiderivative of cosine is sine. So I don't need a minus sign. So that's just sine of the function t. Here, inverse power rule again, I add 1, I divide by 1 plus 1, okay, that's 2. I'm going to add 1 and divide by 0 plus 1, and that's just 1. And then there's one other thing I need to add, which is plus c d, another constant e. Whoa. Whoa. So again, okay, 5 halves plus 1 is 5 halves plus 2 halves. That's going to be 7 halves. So this is equal to 2 over 7. So the reciprocal of 7 halves is going to be 2 over 7 times 4/15 times t to the 7 halves plus 6 sine t plus 1/2 ct squared plus d times t plus the constant e. My god. That is the most general antiderivative It is the third most general antiderivative of that triple prime thing we had. Ask me a question. This is what we did. We started with that. Pause and see if you can recap that process if you have any questions. Okay, friends, so the last thing I want to do is this example, which is also, it's a physics example, but it's also what we call an initial value problem. It's an initial value problem. And what it means is that instead of just using constants, that, unknown constants, we're going to have initial values or information to find what those values really are. Okay, so here we're told that a particle, or maybe think of like a car, I don't know, accelerating. So that means that the acceleration is a function of time. The acceleration is increasing. Wow, that means it's not only getting faster, it's getting faster and faster and faster. And so the rate of change is this linear function. So this car or particle is getting faster and faster, faster. That's what it means. We also know, though, that this acceleration is the second derivative of position. So if we have position, oftentimes that's called s of t. The velocity is the first derivative. Velocity is s prime of t, and usually we can just name that v of t, but that represents the first derivative. And acceleration, therefore, is the second derivative because it tells you the rate at which the speed increases. It's the derivative of the derivative. Therefore, we can call it s double prime of t, and we'll name it a of t. But we can also remember that a of t is the first derivative of the velocity. Which means that if I do antiderivatives, if I take the antiderivative of acceleration, I get velocity. If I take the antiderivative of velocity, I'll get position. So what are we looking for here? They tell us its initial velocity. So how fast was it going right at time 0, right? This is that's why these are called initial value problems, because you know what they are someplace. T equals 0, the velocity, aka the first derivative of position, is equal to -6 centimeters per second. Then also at t equals 0, we're told that s of 0, the initial position, is 9 centimeters. So now I have two what we call initial values. And what are we trying to find? We're trying to find that position function s of t. Okay, so what we're going to do is we're going to first start with the acceleration and do the antiderivative of the acceleration function. I promise it's going to show up here any second. Okay. Oh boy, lo siento. Okay. So inverse power rule. We have a 1 there. We're going to add 1. That becomes a 2. Divide by that number 2. This was a constant, so it gets a first power multiple, and then there's some unknown constant. But notice that c is going to be the initial value of the velocity. So if I just look at this formula and say v of 0, that means that's c. So oftentimes this constant, this unknown constant, is also known as v naught, or the initial velocity. So this is known as the initial value. Because we were actually told what this was, weren't we? We were actually told that v at 0 is equal to -6. So this thing right here tells me that I can replace this constant c with -6. Now I can write the rest of the function down. V of t equals 3t squared plus 4t minus 6. That's my function. And it'll be typed out more nicely here, okay? So I use my initial value to find that first constant. And now I have the velocity function. If I take the derivative of this, right, I should get my acceleration back. Okay, it's going to equal a of t, and that's going to equal 6t plus 4. Okay, which works. Now I have to do it one more time. Take the antiderivative again. Here, notice the power rule is going to increase all of these by, like, so if I notice this 2, I add 1 to the 2, and then and that becomes that. We divide by that number. These numbers, these will cancel out. I have a 1 here, so if I add 1 to that, I get a 2. Divide by the 2, that's going to cancel out. I had a t to the 0 here, so if I add 1, I get a t to the 1. And then I have my constant, the other constant, d, which will be the initial position. Okay. So by knowing the initial position and the initial velocity, I can find exactly the function governing the position of this particle just from its acceleration. Okay? Okay, that's all I'm going to do. It's a long video. I hope you can follow it and that it's useful and that you ask me questions. Okay, bye, everybody.